unit, we're going to be learning how to write a higher order function. So we've been using them in the last unit, and so now we'll go to the next step and see how one is written. So the example that I have here is a function that consumes two things. One is a sequence of integers, and the other one is a function that checks a property of an integer by mapping integers to booleans. So the second parameter p is a function parameter, and so we want to see how do we deal with it. So for example, if I call for all on all integers and I ask, are they all greater than 0, then, since I'm not including 0, then it should return true. If I asked, are they all even, then it should return false because some of them are not even. So there's some efficient ways of doing it, and actually ours is pretty efficient. I shouldn't say that. So we'll soldier on and say, well, the first thing we're going to be doing is we have all of these numbers here, and then we'll just call map on them. And then what do we get? We get a sequence of trues and falses. So in the first case, we'll get the sequence true, 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 true 10 times. The second one, we get a sequence true, false, true, false, true, false. And now we want all of them to be true. And so one way we can do that is we can simply take the and reduce by the and. Notice, by the way, that I say reduce left here, whereas on the previous lesson it said reduce. It's actually more consistent with what we're going to be doing next week to strictly call it reduce left. There is a reduce right for right associative operators, but so technically this is the better way of doing it. So reduce left here means we take the first and the second, and then and the third, and the fourth, and so on. And if all of this is true, then all of them had to be true, and so that's the answer. So here's our function. For all, takes a sequence and a function, and it returns this thing. So it was easy enough to write a function that consumes a function because we simply handed it off to another higher order function, namely map. So let's just try something similar. See how everyone's coffee has been working. So here I have another higher order function, which is called mystery. It takes a sequence and a predicate, and then it does something with it. And I want you to tell me, when does this function return true? Okay, we have a bunch of votes. A, C, A. So, you're not voting? Okay, so the majority answer here is A. That would be the exact same as what we just had, right? And that is, in fact, the right answer. So how can one figure this out? So the first s.map here, that gives you vectors of trues and false. Something like this maybe. And then we're filtering out those that are false. So that means we would be throwing away the trues and get a vector that only contains falses. If that vector has length 0, that's a cumbersome way of saying there was no false in there in the first place. In other words, they were all true. And that means that all the elements fulfilled the predicate. So the moral of this is that, in general, it is not rocket science to write functions that consume something like a predicate or that consume some other function. What is a little harder is to write functions that produce functions And that's what we're going to be turning to now. And in order to put this into an interesting context, let me talk a little bit about comparison functions. So this is something that I'm sure you've seen in C or Java, where you want to sort not just by the natural ordering, but by some general criterion, and then you want to specify the sorting. In Java, you do this by using a comparator. In C, you would be using qsort and passing a comparison function. So in Scala, it's very similar. You would use some comparison function, and the way it works in Scala is that the comparison functions return true if s should come before t and false otherwise. That's a little different than what you have in C or Java, where, if you recall, the comparison functions either return a negative value, 0, or a positive value. Why do they do the thing with a negative, 0, or positive in C and in Java? No. Well, in C there's no true Boolean type, that's correct, but in Java there is. Yeah, because one has to account for the possibility. There really are three outcomes, right? Either one comes before the other, or one comes after the other, or they are equal or indistinguishable. And in Scala, one actually, in some situations, has to make two comparisons. You have to check whether s is less than t and whether t is less than s. And if neither of the two is true, then you know them to be the same. So in some algorithms, it doesn't really make a difference, but in some algorithms, it does. And so the C and Java approach once in a while saves you this extra call. But Scala does, what's mathematically the pure way. They say less than is, it's a total ordering, and the mathematicians have done it like this for 100 years, and they followed the same model. Here we have an example. So when you remember we had the function called sorted. Sorted took a sequence and gave it back to you in sorted order by the natural order of the elements. If you want to sort with some other criterion, you have to pass it as a function. So here we're sorting with underscore less than underscore. So that means we're sorting by the natural order of the strings. Over here, we're sorting by a different way. We're sorting by the length of the strings. So we're saying that shorter strings should come first. So the function here maps s and t, the pair that needs to be compared, to s.length less than t.length. In Java, you would have written s.length minus t.length, but here we just return it true or false, so we use the less than. And when you do that, then they come out sorted by their length. What if we want to sort them by something different? So in this case, I want to sort them by the number of vowels. I want to say a word is somehow bigger if it has more vowels. We don't care about the consonants. So here I'm setting this up. I'm making a function that tests whether a character is a vowel. And it's a vowel if it is contained in the string of all possible vowels. So we're doing it the American way, where we're saying A, E, I, O, and U are vowels. None of this accented stuff that weird foreign languages use. And but it's just a toy example here. And now I want to know what is the number of vowels. I filter out the vowels. So I only keep those that are vowels, and I compute the length that tells me how many there are. So like the word Marianne has 4 vowels, and so the vowels function would give me 4. Now I want to sort by the number of vowels, and that's completely straightforward. I simply say s should come before t if it has fewer vowels. Now have a look at this line and at this line. And you'll see that the structure of these two is exactly the same. I want to compare two things, and I say one of them should come before the other if its value by some function is less than applying the same function on the other. So over here, the function is length, and over here, the function is vowels. So that's what I now want to be able to do. I want to write a function that consumes a measurement like that, number of vowels length, or if I wanted to compare bank accounts, maybe the balance or some such thing. And it consumes that function and it produces a comparator. So this will be a function that consumes the measurement function and that returns the comparator. So how do we do this? So you can write this step by step. So particularly if you have little experience with this is really a good way of doing it. So you just get going and say, the way we've always written a function is we say val, and then the name of the function equals. Then you write down the parameters. Well, what do we know about the parameters? We have one parameter, namely the measurement function, and that produces something. What does it produce? It produces another function. How do we write a function? Well, we write the parameters here in parentheses and an arrow. And then we finally write, what does that function produce? Well, what's it supposed to do? It's supposed to evaluate the measure on S, evaluate the measure on T, and say if S is shorter than T by that measure, then return true. So that's this expression. So when we put it all together, it looks like this. So it's a function that produces another function that produces that. And so you have this very characteristic, the two arrows, because you have a function that produces a function. You'll do that in the exercises, and I think then it'll become clear. So it's one of those things that when you write it, it's actually pretty easy. When you read it, you have to be able to fiddle it apart. So how can we use it? So I can sort the words with compare by of vowels. That's a comparator that compares by the number of vowels. Or I can call sort with compare by of length. I have to write it as underscore dot length, and then it compares it by the length of the string. With compare by, that's what compare by does, is it applies a measure, so I will not get like the natural order of it, but it is a useful thing. This is actually, that's a part of the Java standard library nowadays, and so when you want to compare like bank accounts by balance or people by first name or something, this is a very common kind of construct. So it's a very useful thing, and it's a function that consumes a function and produces one, and I think what's a very natural example. Questions about this? All right, well, we'll see how it goes in the lab, but I also have a mystery here. It didn't look quite as mysterious before, but I was asked to mystify it further, so here we go. So mystery here, what the heck is this? This is a function that consumes two functions, each of which is a comparison function. So it consumes two comparison functions, and what does it produce? It produces another comparison function. And so my question is, what does that comparison function do? And I'm giving you a bunch of choices. So this time I won't go on until everyone has voted. So this must have been hard because I think we've had just about even answers, even votes for A, B, and C. No one voted for D. So let's take this apart here. So we have these two comparison functions, and I find it easier to read when I use math symbols for them. So if I can rewrite this one, I would say this would mean that S is less than T when using the first criterion. Or this one here means T is less than S using the first criterion, and S is less than T using the second criterion. Not T less than S. Oh, so that means okay, not okay. So that means I think I made a mistake here, so that probably would explain. Okay. So T not T less than S. Okay, that means T is greater or equal than S. Okay. No, I was doing it. All right. So, was I? Okay. Let's see. So if S is less than T, then by the first one, then we're also less than. So when do we get into this case here? So in this case, it must be true that. Oh, I see. I didn't want the not, right? All right. So let me answer the question that I wanted to ask, and then we'll see whether any one of these is even true. Okay. So the question that I wanted to ask didn't have the not here. Or did it? I'm such a knucklehead with this stuff. I need more paper. So we had S was less than T by relation 1, or not, and maybe not, T is less than S by relation 1. No, they're subtly different. Give me a second here. So, so what happens if S and T are the same? Then this one is false, right? And what's this one here? If when they're the same, then this one is false. So we're looking right now at the case that S and T are actually the same with relation 1. Right? That's the case I'm interested in. So in that case here, the first one here is false. So I keep on going with the or, because otherwise I'd be done. Then this one is also false. So not of that is true. And I keep on going. And I do actually get to compare whether S is less than T.
Why would it be also false? Because the comparison function only returns true if it's less than, and if it's equal or greater.
But notice that I swapped S and T. Right? So if they're the same, then this comparison is also false. That's the way to find out with whether they're the same, to see whether in both directions the comparison gives you false. When that's the case, then you have two that are undistinguishable. So that means that if they are the same, then this guy here breaks ties. What happens in the case that S is greater than T? Well, then this one is false. This one is true, and then false, and therefore the or is false, and the answer is false. Yes, so in this case here, the answer is false. Okay, so this works like a charm. So in the case that we know the answer, so if S is less than, it's false. True, what am I saying? Because then true, and then the or stops. So in the two cases that they're different, I just get the answer that I get from the first relation. In case the first relation can't tell them apart, then I get the answer from the second relation. And so the correct answer was, in fact, A. That was good. Okay, so I think it was easier the form that I had it at first. With the if, yeah. No. But this was a more interesting exercise because it spread the field further. All right, and I got confused too. So, so it's undeniable that these kind of things are a little bit hard to read, and they take trained practitioners some time to fiddle apart. So you shouldn't worry when you see one of those and you say, "Oh my God!" Just take a few minutes and try to make some sense out of it. It is possible to do it. But the thing that I always find amazing is that when I write them, I don't usually have a lot of trouble. They pretty much write themselves. But then when I come back to them the next day and say, "What have I done?" then it's sometimes rather challenging to find that out. That's just the way it is. But that's okay. And so everyone knows that, and you just then have to take the time to demystify some of these expressions. All right, so now we have a very long lab that, and I will have a break in the middle to see that everyone is on the right track. Where first off, I want you to define some higher order functions. And the first one is pretty easy. The second one is considerably harder. It operates on this comparison function, and your job is to write a function that takes a comparator and returns its reverse. And this is going to be one of those things where, when you first look at it, you may well find it confusing, particularly if you have never done this before. And then when you simply have your fingers type the right answer, you might not even believe that it's going to work, but it will. Try that out. Then we'll go on with the phone mnemonics and get it to a point where we can solve a good part of the problem. We'll be able to do it. We'll be able to get all of the words for a sequence of, we will be able to get the words that match a sequence of digits without without spaces in it. So for example, when we run it on this one here, we'll be able to get Scala and any other things that are also 5-letter words that can be formed like that. I think with Scala there was none other, which is why I used this other one. And now we want to then figure out how to break words, how to deal with multiple words. So for example, when you have this number here, now that you've had all this practice with this, you can probably immediately see that this spells Scala is fun. And but that's the hard part, right? How do you even know where to break it? Maybe there's some other hidden message in there that says, Scala sucks or something. And so one would have to try all possible ways of breaking this into individual sequences. And so that's ultimately what we will want to do. But at first what we're going to be doing is we're going to say, suppose we have a way of having it broken up. So suppose we've arbitrarily decided we're going to be breaking up like this. And then we want to look up the combinations. That one is pretty easy. That one you'll be able to do by using reduce. But the real challenge is, we want to be able to then take this thing and break it up. And so actually there's nothing to do in C. C is just the lead-in to this thing. And it turns out that breaking up is hard to do, and you'll see why. Okay, so let's get going, and by the time that everyone has made it to part 3, then we'll have a pause and make sure that everyone's at the right step before we launch into part 4, which is pretty hard.